Okay, hey everyone, I'm Xiang, and I'm going to talk about the bifurcation analysis of this 2D HH system over here. So actually, most of the parameters of this system are determined by neuroscience experiments, and the only thing we are interested in is that how the behavior changes along with this I over here. So the I represents the injected stimulation to this neuron, and that is something we can change in real neuroscience experiments. So firstly, I simulated the system using some different values of I, and all the simulations are run using a forward Euler method. Okay. So firstly, I tested the I equals to 2.5. And in this case, we can see that the axis represents the time, and the y-axis is this membrane potential represented as this Vn over here. So if I equals to 2.5, then we can see that the membrane potential converges to a certain value and it stays unchanged. And in the phase plan, the trajectory converges to a sink or maybe a stable equilibrium in this case. Okay. And if we increase the stimulation a little bit to say 3.0, then the behavior will be totally different. So we can see that instead of converging to a certain value and stay unchanged, the membrane potential changed periodically, and there is some spikes in the solutions. And the peak membrane potential is about 120 volt. Okay, so since the solution is periodic, so we can see a limit cycle in the phase plan over here. Okay, so the red dot here represents the initial point. Doesn't make any difference. So from this figure, from these results, we can tell that the behavior of the system is really different with different stimulation I. Okay, so in order to find out at what point does the behavior change, I use this increasing stimulation input to the neuron. Okay, so the lower figure represents the stimulation I injected in my simulation. So okay, so this can be done similarly using Euler method, by the way, because we can. So this is still a parameter, but it's just changes with t, and it makes no difference if we use Euler forward method. Okay, and so the stimulation starts from 0, and we can see that when the stimulation is really small, the neuron will be in a resting state, and there will be no spike. And if it passes some value, then the neuron will begin to spike periodically. Okay, so apparently there is some kind of threshold over there, and so the thing is, we cannot tell what the threshold is exactly just from this figure, because there's some kind of lag in this case, in this situation, because if the stimulation increases past the threshold, then the neuron will not spike immediately. Okay, there's a lag in this situation. So, but we can tell from these results that the threshold is somewhere between 2.5 and 3.0. Okay, so I just roughly plot a threshold over there. So this threshold is the minimum stimulation we need to generate spikes in this neuron. Okay, so mathematically speaking, this threshold is actually a bifurcation of the system. And in this case, it is a saddle mode bifurcation. Okay, so if the stimulation is larger than the threshold, then there will be a limit cycle in the trajectory. So I plot the limit cycle for different stimulations, different values of stimulations, and we can see that as long as the stimulation is larger than the threshold, there will be a limit cycle in this phase plan. Okay, so the way to do this is just we run the simulation and it will converge to this limit cycle. This has been done in the homework for a lot of times. Okay, so a very unexpected phenomenon is that if we increase the stimulation, the peak membrane potential will not increase, and instead it is decreasing. So for example, if the stimulation is 5.0, then the peak is about 120. But if the stimulation increases to 200, the peak membrane potential is even less than 100. Okay, so this is not very intuitive for me, okay, because for my intuition, if the stimulation is stronger, then the spike will be more dramatic. Okay, will be more dramatic. So that intuitively, the peak membrane potential should increase if we increase the stimulation. Okay, I think there's some explanation behind this, because it seems not the case in reality. Okay, and another thing is the period of the limit cycle. Okay, so the period of the limit cycle is actually the time interval between each two spike. Okay, so this represents the frequency of the spikes and the frequency of the spiking. So this result is what I expect, because if you increase the stimulation, then the frequency will increase, and the time interval between each two spike will become shorter and shorter. Okay, this is very intuitive. And another very interesting phenomenon is that if we further increase the stimulation, we may expect that the spike will be stronger and stronger. The spike will be more and more frequent, but that's not the case. So if the stimulation increases to like 400, the spike will disappear. Okay, so the neuron returns to the resting state as before. Okay, and I have absolutely no idea what the biological physical explanation for this. Okay, so you can see that, for example, if the I equals to 400, the limit cycle disappears and the trajectory returns to a sink or a stable equilibrium over here. Okay, so again, I used increasing stimulation to find out where the threshold of this phenomenon is. So we can see that. So in this time, I start the stimulation from 300, and at first the neuron spikes, very frequent. And if the stimulation keeps increasing and it passes some value, then the spike will disappear and it converges to a certain value of the membrane potential. So again, the threshold in mathematics is actually a bifurcation, and in this case, the bifurcation is a Andronov-Hopf bifurcation. Okay. Okay, this is all the results I have. Thank you.